LTX 2.3 has just been released, and without a doubt, it's another major milestone in the open source video generation space. Compared to the previous 2.0 model, 2.3 bumps its video parameters from 19B up to 22B. It now offers much better support for 916 vertical videos, and it brings clearer audio, more stable image to video conversions, smarter prompt understanding, and much crisper text rendering. However, just like the 2.0 version, its biggest drawback remains the same. The model is still quite bloated. In the open source community, there are various application solutions designed to help video creators generate higher quality videos using less VRAM and in less time. In this video, I'm going to provide you with 3 different solutions. You can choose the workflow that best fits your actual hardware and computing power. To help you clearly see the differences between these 3 methods, I used the exact same prompt, the same reference image, and the same seed to run a standardized test across all of them. There are also a few quirky details to note here. For instance, with this new model, even if you are doing text to video, you still have to provide an input image. As you can see, the new LTX 2.3 provides quite a few models. First, we have the full precision model. Then we have a distilled version, which is mainly designed to speed things up. If you use the distilled model, you can set the CFG down to 1, run it for just 8 sampling steps, and get a fantastic result. They also provided a LoRA. You can use this LoRA in combination with the full precision model to achieve the exact same speed-up effect as the distilled version. The remaining 3 models are upscaling models. 2 of them are for spatial upscaling, meaning pixel upscaling, and the third one is for temporal upscaling, which is basically what we call frame interpolation. Currently, comfyUI already supports this model. This is an official blog post from comfyUI, and you can find the workflow download links right inside it. Make sure to update your comfyUI to the latest version. Click on the Templates button. Select the corresponding model from the drop-down list, and you'll see 2 workflows, one for text to video and one for image to video. For the sake of this demonstration, I've also built these workflows on Running Hub. In the comfyUI space, Running Hub is a fantastic online cloud platform because whenever new models or extensions drop, they are always the first to support them. It also provides a great online community for comfyUI creators, where you can find tons of practical workflows and creative inspiration. Alright, let's first take a look at the official LTX 2.3 image-to-video workflow provided by comfyUI. The basic structure of this workflow is actually very similar to LTX 2.0, just with a few parameter tweaks. First, we need to input an image. This image can be landscape or portrait, but pay attention, make sure the width and height are ideally divisible by 32. Also, the total frame count must be a multiple of 8 plus 1. In this workflow, they've also listed all the download links for the models and clearly explained exactly which local directory to place them in after downloading. Right here, there is a switch to toggle between text to video and image to video, which is super important. Here is our total video frame count, the resolution settings, and the frame rate setting. I've set it to 24 frames per second here. Next, let's look at loading the main model. Notice that I am currently loading an FP8 version. This model was officially released by LTX, and as you can see, it is nearly 30 gigabytes. The full precision LTX 2.3 model is a whopping 46 gigabytes. So we have good reason to believe that the FP8 model wasn't just created through a simple data conversion. Running this model on a consumer-grade GPU is still going to be quite a challenge. Since this specific model doesn't have built-in distillation, to boost our speed, we're using the official Distilled LoRA, setting the weight to 0.5. Another crucial thing to note is that when loading the main model, we aren't using the standard diffusion model loader. Instead, we are using the checkpoint loader. This means that inside this model file, besides the main model itself, there are other components. Specifically, it contains the video VAR therefore. We need to extract that separately. We also have our audio VAR here. Moving further down, we have our encoders. For the first encoder, we're using Gemma 3, just like in version 2.0. The second one is a dedicated encoder specifically for LTX 2.3. Next up is our upscaling model. We are using spatial upscaling here because right now people generally care much more about visual clarity and resolution rather than frame rate. When it comes to your prompt, it must strictly describe your reference image. This prompt roughly describes a hot summer day where a beautiful woman is taking a bottle of mineral water from her companion's hand. For our audio design, we wrote, "I need that." After our prompt gets encoded by the text encoder, it feeds into this node called LTX-V conditioning. We actually used this exact node back in LTX 2.0. Below that, we have a custom sampler using an Euler variant. Next are our sigmas. This is quite unique because it is a manual sigma setup, meaning the sampling steps are actually hidden inside here, so you don't need to explicitly set the step count yourself. The most critical part here is the latent image, which is tied directly to our reference image. Let's look at how the reference image is processed. First, we scale the input image to align with our target resolution. The following process is identical to LTX 2.0. We scale the long edge to 1536, compress it, and then halve both the width and height. As we all know, LTX workflows basically operate on a two-stage sampling process. It first generates a video at half the final size, and then upscales it to your target resolution. Next comes the latent generation. For the audio latent, we just generate an empty one. For the video latent, we also start with an empty one, but we need to inject our reference image into this latent space. Then we combine the video and audio latents and pass them into our sampler. At this point, we get our baseline sampled video. In this video, the audio is fully generated, but the video resolution is only half of what we want. So we need to further upscale the video. This is where our upscaling model comes in. As mentioned, there are two types of upscalers, spatial and temporal. Since we are doing pixel upscaling, we use the spatial upscaler. There is a 1.5x and a 2x M modal. We chose the 2x upscale model here. We then separate the video latent from the audio upscale it, and then do something very important. We re-inject our reference image into this upscaled latent to ensure overall character consistency. Then comes our stage 2 sampling. It is mostly the same as stage 1, but notice that the sampler and the sigma step count are slightly different here. After sampling, we separate the audio and video latents once again because they require different VAAs for decoding. Finally, you get your ultimate generated result. Let's take a look.
I needed that.
Overall, the quality is quite good. This generation took me exactly 2 minutes and 40 seconds, so the overall speed is quite fast. From this simple test, you can see that compared to 2.0, the LTX 2.3 model has massively improved in generation speed. In terms of quality, the generated characters look much more natural and the audio is noticeably clearer, though there is still a tiny bit of noise. However, the biggest issue with using this specific workflow is the massive VRAM footprint. This setup requires almost 30 gigabytes of RAM. If your GPU doesn't have enough VRAM, you should definitely try the second solution. This second workflow is provided by Kijai. As you can see from this screenshot, the main difference is that the video VAE has been completely separated from the main model. They've also optimized how the text encoders are loaded. You can download the corresponding models directly from his Hugging Face repository. He provides several versions of the main model. Pay attention here. The ones with the distilled keyword are our distilled models, which run faster, but aren't necessarily smaller in file size. For file size, you need to look at the precision. We have BF16 and FP8. You'll also notice other keywords like scale and input scale. What is the difference? The technical description is a bit complex, but simply put, if you have an RTX 40 or 50 series GPU, use the input scale version. If you have an older GPU, just use the standard scale version. Let's look at Kijai's workflow in comfyUI. The main difference lies in how the main model is loaded. Because the VAE is now separate, we can use the standard load diffusion model node to load the main model. Because of this, we now have to load two separate VAS. Down here is the encoder loading. We are still using Kijai's strategy here, which relies on a model called text projection. When loading your second encoder, just select this one. The upscaling models remain exactly the same. Let's run it and check out the execution result.
I needed that.
I think the output result is just as good as the official version, but the main model size dropped from 29 gigabytes all the way down to 23 gigabytes. Next, let's take a look at the GGUF workflow. Once again, the difference is in the main model loading. Here we are, loading a Q4 model quantized using k-means. Where did this model come from? It is from the highly renowned QuantStack. In their model list, you'll see a massive variety of models, ranging from the absolute smallest Q2 all the way up to Q8. We chose the Q4 k-means version here, which is nearly 18 gigabytes in size. You can pick different quantized models based entirely on your own computing power. For the video and audio VRAMs, we are still using Kijai's loading method. For the encoders, we use the GGUF dual encoder loading node. Note that the Gemma 3 model we loaded here is also a quantized version, sourced from Dreamfast. Because this encoder is inherently quite large, I highly recommend using a quantized version to save space. They offer everything from Q3 up to Q8 fast, so pick the one that works best for you. Let's check the final generated result for this one.
I needed that.
You'll notice that because the character makes a very pronounced head-turning motion in this video when her face turns back toward the camera, her consistency shifts a bit. I haven't fully tested if this specific issue is caused by the quantized model, but overall the baseline video and audio generation quality is still solid. Finally, let's talk about text to video. Regardless of which workflow you are using, if you want to generate text to video, all you need to do is switch this toggle to true. Ultimately, this setting impacts this specific node. It is actually very easy to understand because there is a bypass here. It determines whether or not our reference image gets injected into our latent space. If you set it to bypass, it means that no matter what image you input here, it won't affect the latent space at all, and therefore won't affect the sampling process. Let's use the same workflow parameters and run it again for text to video.
I needed that.
You can see the realism is incredibly strong, right down to the character's breathing sounds. However, you'll notice that the new LTX model still has some slight issues with rendering highly detailed physical actions. For example, look at the action of twisting the bottle cap. There isn't even a cap on the bottle anymore, but she is still making the twisting motion. So the underlying physical logic still needs some optimization. Alright, those are the 4 different workflows we covered today. These represent the most fundamental applications of LTX. Later on, we'll show you some even more interesting and advanced ways to use it. That is all for today. Follow me to become someone who truly understands AI.